morning to everybody. It's a pleasure to be here today. And the topic of my TEDx is about what to do with small satellite in large quantities. You may have heard in later years that satellites are becoming smaller, and people are talking about thousands of them in constellation in space. What is going on? Why this is happening? And most important, what can you do with this new idea? So, a brief history of technology over the last 60 years. So, brief history of computer. In 1946, the ENIAC was large as this room and was making simple computation, addition, division, multiplication. Then we had the PDP and VAX. You don't know what they are because I was working with them. You were not yet born. And then we had the portable computer, no, sorry, the desktop computer on a table. Then you had the portable computer. And then in the coming years, every year there is a reduction by a factor, which diminishes the volume, the power, and increase the computing power. Over the last 70 years, something incredible has happened with the computer. Everything gets smaller and more powerful. Cellular phone, this happened in many technologies. Cellular phone, in 1973, this large unit was the first wireless phone. Then the time went on, and today the phones are very small, very powerful. The size of the phone is defined by the size of your hand. You cannot make phone much smaller than that because you don't know how to touch them. They could be much, much smaller of the same power. They can do many things. Your portable phone in your pocket can do something which was totally impossible to think a decade ago. Somebody says that the current cell phone have more power than the Apollo program altogether, to have an idea of the comparison in computing power. So, satellites. Satellites is a technology we started about 60 years ago, the first Sputnik. And today, they can be large, very large. Telecommunication satellite in geosynchronous orbit, the one which gives us television and internet and telecommunication on digital scale, are very large, could weigh 5, 6, 7, up to 8 tons, thousands of kilograms, and takes many years to be built and hundreds of millions of euros or dollars to be conceived and deployed and built. But today, satellite can also be very small because the same technology development which happened for computer and for cell phone and for many other very available technologies is happening also obviously on satellite because everything can be smaller with the same power, even increased power, and with a decrease in cost, which is tremendous. So CubeSat, what is a CubeSat? Is a definition of a dimension 10 by 10 by 10 centimeter, more or less. This is a basic CubeSat. This is 1 unit. 2 units is 20 by 10 by 10. 3 units, 6 units is 60 by 10 by 10. So CubeSat are becoming today like the personal computer became for the space industry, for the Earth-based electronic industry, consumer industry. But this is happening in space. So the question is, what can you do with those small gadgets in space which can be built for a fraction of the cost of the last satellite, but have a power which is comparable to the current technology in electronics? In 2011, 7 kids, youngsters like you, drop out school, Silicon Valley engineers founded a company in a garage in Silicon Valley, of course, was Planetlab, and they had the idea, let's do it. Let's build small satellite to look to the Earth. I mean, satellite obviously can take beautiful images of the Earth, beautiful picture. Let's do it, let's build satellites, find a clever way to do them cheap, and a clever way to put them in space and take images of that. Brilliant idea. They worked together, they started that, and a few years after, in 2014, 3 to 4 years after, they managed to launch 28 of those satellites called doves. This is a bird which is looking from the top, from the ISS, the International Space Station. The International Space Station is a bright idea in the bright idea, because using the International Space Station to launch satellite is not exactly the way it was conceived. The space station is a home for astronauts to operate in space, to make large experiments, to do a lot of things about floating around in microgravity. It was not the right place to launch things, but somebody realized, another group of kids started a new company which was exactly dealing with NASA, a special agreement to find a way to launch small satellites from the International Space Station, and they did that, and the two together. So this is one of those satellites, the Dove, you can see, is something you can have in your hand. It must be a 6-unit or a 4-unit long satellite. You can figure out the power panels, the cameras, some stabilization, and this is
4, 3, 2, 1.
This is how the satellites are launched from the station. And you know how they are launched? There is a spring, a mechanical spring, which is inside this kind of cannon, and they are pushed out 2 by 2, and they go to orbit, and they start orbiting around the Earth. They are launched against the motion of the space station to be below, at a lower orbit, so they can operate at about 400 kilometers of height. And what you do with that? You do a constellation, which after this first 28 went up to 77 total, align one after each other, or looking down to the Earth, passing, since the full orbit is 1.5 hours, and you have about 100 of them, every 9 minutes or so, sorry, every 90 seconds or so, few minutes or so, you can have a new satellite coming over the same location while the Earth is turning, and you can make precision, frequent observation of all kinds of places on the Earth, and this can be on a daily basis. This is new, because satellites which observe the Earth are typically one, which is coming over a single location, typically once a day, but is focusing on a single spot. So the real repetition of a satellite to take a picture of the Sant'Anna building is typically 16 days, because the next time it's passing as a slightly different latitude and longitude, and then it takes a different images. Unless it can point, focusing on the same spot, if it is not just scanning, it's passing over the same location typically once every 2 weeks. These every day make a complete image of the Earth, and with the repetition time, which is a few minutes. What you do with that? Oh, many, many things. You have to scratch your head and find what you can do with that. For instance, if you take picture of a refinery, oil refinery, gas storage, you know, these storage tanks, you can see they have shadows. The shadows is given by the light impinging on these storage vessels at a given time of the day, and depend on the height of the top of the vessel. If you pass with the satellite at the same day, every day, and you count the shape, the area and the shape of those shadows, you can say which one is going down, by how much, which one is going up, which are the reservoir, and then you call the stock market and you plan to invest in the future. This is a highly economical information, and it's based on the fact you can, on a daily basis, take a picture of all the tanks storage in the United States, as an example, or in China, and make your model, find the information, and use it on the stock market. And indeed, this is what the company Digital Globe is doing. This is a 2016 announcement of that, who's using the output in 6,000 industrial plants in China. The resulting data get collected, integrated in the manufacturing forecast, which Bloomberg is providing to these terminals. Great. This can only be done with a lot of observation taking place on a regular basis over all the world. In this particular case on China, was not possible to do with one single satellite passing over a certain location every 16 days. But you can do many things. For instance, you can see how a refugee camp in Uganda is developing over weeks. It's impressive. Yeah? This is the background is changing because the season is changing, but you can see the amount of tents which have been built over a few weeks of time. And this is very important to international relief agencies, because sometimes those camps, since the world is very large, you don't even know about that. And taking picture of all the Earth, you can learn about changing patterns of many kinds, not only oil storage tanks, but also people, refugees escaping from a difficult situation. Or you can spot rapid deforestation pattern in the Bolivian rainforest. This happened over a few weeks, and you see how quickly this particular spot has been eradicated from all the trees to create some field for agriculture or whatever. Again, because you are measuring continuously in this hidden spot on the Amazonian forest, the changes day by day, and that is clearly visible. Or you can monitor, this is over a longer time, how a certain city is growing, in the meantime, how the reservoir of water are going down. This is more like about monitoring mega cities and resources of water, meaning there are plenty of things that you can do to the extent you can regularly visit all over the Earth, and without having predetermined objective, just monitoring the changes over and over and over, and many of that has an economical value, a refugee type of value, protection, intervention value, urban planning, and so on, and so on, and so on. This is the desert being populated by irrigation field. You know these circles, each of them is water being poured to grow in the desert some agricultural field. And also in this case, you can see weeks by weeks how things are developing. They're also very beautiful geometrically, but it means this is taking place a very large change in the way this particular spot of the Earth is being used. But you can see the most incredible things which never before have been observed. You see this is a river. You can see it is changing flood. But this one is a new river being created over days. This new river is finding out its path, was not there before, and has been observed starting and creating and burning and eventually getting somewhere to the next river or to the sea. These kind of things also escape observation because normally you don't have the capability to do it. In a random place of the world, at the right rate, you can understand what is going on. In the future is today. If you have those constellations of many satellites, what will you do? Easy. You go from Google Earth static, photographs, typically a few months old, to Google Earth dynamic, the Lumiere version of Google Earth, where things keep moving. You observe cars, ships, plumes of industries. You see the world at the size and over the time scale that you need to really understand about our life. Observation of the Earth today is about weather change, climate change, weather condition, relatively large structure which respond to the way Earth developed. But today we are getting down to the scale of time, or the scale of size, which is typical to the human behavior, and this has tremendous economical implication. And you can do that only if you take over and over and over images and then interpolate that, and you create a movie having the right step in observation. Now, this is maybe the most successful story about Planetlab. By the way, in 2014, after they deployed the first 28 plus 50 doves, they got to the stock market with $220 million investors' money. So, I mean, it was a great success by these people, which are not anymore 7, but they are probably 700 today, and they keep going very strong. An interesting feature of most small satellites, a dove weighs about 5 kilograms. 5 kilograms, 3 PCs. Is that they are so inexpensive that you can have iteration. One after the other, you build the first one, you try it, a small constellation, you understand something has to be improved, you throw it away, you start from scratch. I was talking with one of the CEO of this company. He says, look, we are building a 20 satellite a week. To create a constellation of 80 satellites takes 4 weeks. We don't start the construction unless we have available a launcher which can launch us, because launcher is the bottleneck today, not the satellite anymore. So if you take 100 satellites at 5 kilograms, it makes 500 kilograms. It's a small satellite by the standard of the several tons one. So even 100 of those satellites, which is the largest constellation today on the sky, is a fraction of the weight of large satellite. And if you take the cost of those units in the 10,000s of euros, if you multiply with 100, you still have a cheap amount of money with respect to the multi-hundred million investment which is needed for large satellite. On February 15 this year, 2017, was a launch of a PSLV, which is an Indian launcher. Look to this one. This one is called Dido, but the other is a second constellation of Spacelab. So they launched another 85 or so, and they replaced the previous constellation with a new one, and they are now taking better observation with a newer generation. But in the same launch, one of those satellites, this PSLV launch deployed 105 satellites, about 85 for Planetlab, one, this Dido, which I will talk in a moment, plus another 10 or so for other customers, in one single launch, 105 small satellites for different purposes, and one was a constellation. But one of these is another application, which I found really remarkable. Dido is a 3-unit CubeSat, so 30 by 10 by 10 centimeter, which the first part carries some control system, power system, computing, and telecommunication. But the second 2 units contain 4 chemical laboratories, biochemical laboratories. I don't know if here there are people working in this field. Probably yes, because you do have this kind of studies here. So, you know, chemical laboratory, biochemical laboratories to build pharmaceutical new molecules and to study their performance, how they can be folded, and so on and so forth. And there is an understanding of the fact that in absence of gravity, meaning in free fall, where the gravity does not play any role, and there are no convection activities during the chemical reaction, a cold part of the liquid or the gas and the hot part of the liquid or the gas have the same weight. They stand still, and there is no mixing about different parts. So people believe that with the absence of gravity, certain molecules can be built in space either without defects, crystals of complex molecules without defects, or folded in a different way. So typical biochemical labs can be large, but microelectronics, micromechanics, microdetectors can squeeze it down to a total size of about 20 centimeters of height, 10 by 10 in square, and inside here you have whatever you need to do your biochemical experiment. But which is the advantage that you can do from your desktop, controlling remotely what is happening up there. On the International Space Station, this kind of experiments were done on a rack, which were weighing 100, 200 kilograms, with an astronaut pushing the keyboard to do certain sequence of things. Here, everything is squeezed down to within a small satellite with scientists, not astronauts, students, working on their desktop to repeat over and over different experiments, to do hundreds of experiments where the International Space Station was doing a few because of the complexity of the cost. So we believe that this will be, number one, able to provide very precise crystallization of complex protein and different molecules without the defects induced by the effect of the mixing due to the heat differences on Earth. So this is going to create a certain class of new highly purified pharmaceutical. But even more fascinating from the point of view of the implication is what about the folding processes of certain type of molecule typically related to the strands during the DNA or RNA multiplication. You know that folding is a very complex system. Understanding how folds behave requires very powerful supercomputer, but we understand that it's so critical about the initial condition that if you change the initial condition in a significant manner because gravity is gone, folding can take a different shape. And the folding of a large molecule has to do with this capability to have pharmaceutical effects. If you change the shape of the molecule, it can be totally useless, or maybe can be very important for certain other application. And companies during the pharmaceutical development are very much interested to understand all the possible folding of a given molecule, to patent it. So Dido is already realizing now studies of this kind for a number of pharmaceutical laboratories or companies, which for the time being are studying those different folding situations, patenting new folding conditions. The only thing they cannot do today is to bring back the result, because once the folding is done, it's stable. But this is the future. In the future, we'll have factories in space which can do that on larger scale and bring it back. So this is just a preparation for the next phase. So these are just two examples, which I hope they made some sparks in your imagination. But in reality, nanosatellite can accomplish many different things. And literally, there are many new possibilities, and only sky is the limit. This is a new tool, which is less expensive, can be modified, tailor-made, because as a function of the need, it can be redone over and over and over, and this scale of small companies, even universities, is huge scale. But the ideas are the most important thing. So if you look around what can be done with this constellation of small things, many things. Quantum key distribution. Banks need to have ultra-safe key distribution system, and as you know, through fiber optics, you can hardly exceed 100 kilometers, and then you have to regenerate the information. The moment you regenerate the information, you lose safety because there is a point where some electronics is doing certain operation. So it's much more convenient to send the crypted key to the satellite, to deploy the key to a network of banks, and then using this key, which has been transferred on a safe channel, you can then start the transfer of the big quantity of data protected without a public key transfer. Example. You can look to many things on the ionosphere, on the atmosphere, on the magnetosphere, on the same time on different locations. Example, a meteorological satellite. We base our life on the prediction of meteorological satellite. If I ask you how many they are, just a few, 6 or 7. Large satellite on geostationary orbit providing this information to everybody. You can have a meteorological satellite now in dozens, in hundreds, taking pictures more precise on a different scale, and this will improve the quality, the details of the capability of predict the weather. You can find many possible activity, and what is important, not each of those applications is not multi-purpose. It's focusing on something, because the cost is so small that you can focus on tracking vehicle and forget about agriculture, or about desertification, forgetting about anything else. And and so on, and so on, and so on. Again, is tailor-made space application. So there need good idea, some degree of technology, some degree of investment, but I see in the future, we see in the future that mega constellation or constellation of small satellites are going to change the way we do space. Thank you so much.